Can I put this down? Let's go down. Good evening, everyone. The India International Center is privileged to welcome renowned astrophysicist, Professor Priyamvada Natarajan, who will be speaking on unveiling the first galaxies and the first black holes. Professor Natarajan is Joseph S. and Sophia S. Fruton Professor of Astronomy and Professor of Physics, Chair Astronomy and Chair Women Faculty Forum, Department of Physics, Yale University. She has made seminal contributions to our understanding of the nature of dark matter using gravitational lensing studies and the assembly history of supermassive black holes over cosmic time. She is the current chair of the Department of Astronomy and an external PI at Harvard's Black Hole Initiative. In addition to her research work, she is deeply invested in interdisciplinary scholarship and public dissemination of science. The recipient of many awards and honors, including fellowships of the APS, AAS, AAAS, the Guggenheim and Radcliffe Fellowships, she was recognized with the 2022 Liberty Science Center Genius Award and 2025 Danny Heinemann Prize in Astrophysics. She was included in the Time 100 list of most influential people in the world in 2024 for her path-breaking contributions to astrophysics. She has served as chair of the National Astronomy and Astrophysics Advisory Committee that advises NASA, the U.S. National Science Foundation, and the U.S. Department of Energy. Dr. Natarajan is the author of a critically acclaimed book, Mapping the Heavens, and is currently working on her second book. Welcome, Dr. Natarajan. The chair for this evening is Life Trustee of the IIC and Director of the National Institute of Advanced Studies, Bengaluru, Dr. Shailesh Nayak. He is a prolific writer and editor-in-chief of the Journal of the Indian Society of Remote Sensing. Dr. Nayak was the chair, Earth System Science Organization, and Secretary to the Government of India for Ministry of Earth Sciences and former Chancellor of the Terry School of Advanced Studies, Delhi. He provided leadership for the programs related to science, climate change, weather services, polar science, geoscience, ocean science and modeling, ocean survey, resources, and technology. Welcome to you, Dr. Nayak. Before I invite Dr. Nayak to take over from here, I invite Ambassador Shyam Saran, Life Trustee and President IIC, to felicitate Professor Natarajan. Very important request. May I ask everyone to put their phones on silent mode or silent altogether, or put it off? Thank you.
Good evening to everybody. Very happy to welcome Professor Natarajan, a very famous astrophysicist, and to IIC. And I also acknowledge the presence of our President, Sri Shyam Saranji, our Director, Srivastavji, Meenakshi Shyam Bajpai, and many other distinguished members. It's really fortunate to have Priyamvada Natarajan here, because in IIC, what we say, where the ideas grow. And she's full of ideas. I mean, whatever she has done in her life, it starts with an idea at a very young age. Maybe she may be in a school at that time to today. And that, I think, the ideas converted into various theories, then validated models, and then we learned many things about the galaxies and whatnot. For most of us, this dark matter, dark energy, galaxy, we are completely dark about it. We may be knowing only by words. And I'm sure that today she would throw light on those and enlighten us about what is all about. 3 o'clock, when I learned very important thing, that she is fascinated by the maps. And this is something very important because normally the physicists are far away from the maps by and large. It's more of a geography, geology, those who deal with the maps. But when I thought it's very important because map provides a relationship between the different objects, different aspects, the various processes, and of course, ultimately it will provide connection to the humanity. So I think this is very important lesson which I learned today, that why maps are so important in this. Apart from writing a very famous book, the one thing which is very important, that are TV shows on the black hole acolytes. I think I was told that it is very popular, and this is something which is sees her personality, which is quite unique. Also, I have learned that the most of the great scientists, if you take in India, either Baba or a Ramanna or a Vikram Sarabhai or a C.V. Raman, all were extremely good musicians as well. And I think she is also, I was told that she is a Bharatanatyam dancer, she learns music. And I think this is the connection, the creativity, either in the arts or the science, is all the same. And that is why she is heading both art and humanities together. And that is, I think, is very important because ultimately the science has to lead to the betterment of the humanity. Some of the questions which we have about this, I'm sure that she will provide the insight into those things. And also, I think the important thing is, we would like to understand later from her that there are many issues which physics can't answer. And then I think the philosophy starts. And I think she is also developing on the philosophical side of this, which is, I think, is extremely important. So I think we are going to have a great treat in understanding these galaxies. And may I invite you to deliver your talk, please. I thought it's mine.
This. Sorry. Close.
Yes, thank you. This good? Okay. No, it's not. Okay, first of all, I want to say how honored and delighted I am to be able to speak today to all of you. It's a real privilege to be able to share and tell you more about the work that me and many others like me have been doing for the last decade or so, sort of work at the cutting edge of astrophysics. But before I move on to say that, I want to say a big thank you to Dr. Shyam Saranji for this invitation and for everyone at IIC who worked to make this happen, and for all of you who are here. And I want to say give special homage to my mother who's here in the audience. And obviously, nothing would have been possible without my parents, and this is an occasion where I really miss my father, whom I lost a year and a half ago. And anyway, so what I want to tell you about today is the kind of radical transformations in our understanding of galaxies and black holes that the James Webb Space Telescope has wrought in the very few years that it has been operational. And in particular, what I hope to sort of show you and share with you is that there's something really fantastic that is happening in all sciences right now, and particularly in astrophysics and astronomy. And that is, we are in a very, very unique time where the pace of discovery is so rapid because of this sort of confluence of ideas and instruments that, enabled by the advances in computation, that have really kind of brought to fore new tests, new ways of validating ideas, frameworks, concepts, that is just revolutionizing all of science. And what is special about today is that the time taken between when a scientist is able to propose an idea, propose a concept or a new way of thinking about something, and the time within which it is actually experimentally, empirically validated has shrunk remarkably. So today I'll be talking about something that has happened in my own lifetime. I'll be sharing ideas, some new ideas that I had proposed when I started as a junior faculty at Yale in 2005, 2006, and that I was very fortunate, and as I often refer to it as a real gift from the universe, were actually validated a couple of years ago. But before I do that, it would be remiss of me to not connect what I'm doing with India. I'm really grateful for all the advantages. I had the privilege of being born in a very supportive academic home that gave me my start, that encouraged my curiosity from a very young age. So it turns out that the origin of the term black hole is actually from Calcutta, and that this was well before the astrophysical object was actually found. Before we had the concept of black holes in astrophysics, there was a prison, an infamous prison in Calcutta, where soldiers from the East India Company were imprisoned one night, and it was a point of no return, i.e., not a great prison to have ended up in. And this was 1756. And this term, it was called the Black Hole of Calcutta, and this term actually existed before astronomers had actually come up and understood what a black hole was. And the idea of a black hole, of course, comes from Einstein's theory of general relativity, and the profound insight that he had about this really intricate relationship between matter and the shape of space, and the interplay between them, which is what gravity is. Newton's theory of gravitation and law of gravitation actually tell us how gravity works. So it's the force of attraction between two objects. It falls off as the inverse square of the distance between them. But it doesn't tell you what gravity is. It just tells you how it works operationally. And Einstein's theory is the one that actually expounded and explained to us that gravity is the interplay between the shape of space itself and matter, and it emerges as a property of this combination. And so what is a black hole really? So a black hole is the distortion that is produced in the shape of space when you concentrate a lot of matter into a very, very tiny space. So a black hole is actually a very special region of space where you have a lot of matter that is concentrated. And the impact that it has on the shape of space is that all matter, we all live in a four-dimensional sheet, which is our universe, 3 dimensions of space and 1 of time. This, again, is a construct that Einstein gave us. And any matter in the universe causes a little pothole in this shape of space, in this sheet. Now, how deep that pothole is, unlike the ones that you encountered driving here in Delhi, depends on the mass of the object and how densely packed the matter is in that object. So here you see a little cartoon showing that, you have a little pothole that the sun makes, and then a neutron star, which is much denser and more compact, makes a much deeper pothole. And if you sort of move along this line of thinking, what a black hole really is a puncture in space-time. It's a deep, deep, deep pothole in space-time. And it has a very peculiar property that at the end of this puncture, you have a region, a singularity. It's a place where all known laws of physics break down. So we have no description, we have no understanding of what goes on there. So that's what is very peculiar about a black hole. And this is a reason why Einstein himself did not like the idea of a black hole. And it turns out that Einstein's equations are actually 10 equations that are kind of coupled together. And when he wrote them and presented them at the Prussian Academy of Sciences in 1915, he never imagined that anybody would find an exact solution. It was way too complex, he thought. There wouldn't be an exact solution. And it turns out that Karl Schwarzschild, who was a physicist but was in the trenches, this was World War I was raging, and he heard about Einstein's lecture, he got a transcript, and he worked out at the battlefront, when he was actually fighting, between spells of fighting, he actually worked out and found the first solution. And the solution is the shape of space around a very, very compact piece of matter, what you see there. And so Einstein, he wrote to Einstein, and Einstein said, oh, great, this is very interesting, but I don't think this is real. It's a nice mathematical curiosity, and it's not real. Well, it turns out that black holes are actually real, and what you're seeing here is a simulation from one of the NASA labs where you are seeing light rays that are skirting around a black hole. And we're just tilting it to show you many different views. So this is light just circling around, and you see a very sharp kind of surface, a circle in the center, and that's called the event horizon. So for any of you who saw the movie Interstellar, you can kind of see this is what sort of Gargantua was, right? You saw this kind of image. So this is an actual scientific calculation. In fact, in the movie, they did scientific calculations. So what really is a black hole? Why are these objects so enigmatic? So that's sort of 3 different ways to think about them. One of them is the strength and the pull of gravity. So you have a notion of escape speed from the grip of gravity. So for example, when you launch a rocket from either Cape Canaveral or Sriharikota, the reason you need rocket fuel, you need to boost it, is because the escape speed to move away from the grip of Earth's gravity is about 11.2 kilometers per second. So that's what you need to boost the rocket with. Now just imagine if that escape velocity was actually the speed of light. For that case, not even light can actually escape the black hole for any velocity, right? Now that's a black hole. So black hole is a region from which once light crosses into this region, it can't escape. And for that reason, we can never directly image a black hole, which, for astronomers is a bit of a bummer because, we like to see beautiful visual images, but this is a quantity and an entity, a cosmic entity that we have to indirectly infer its presence. So another way to think about black holes is as stellar corpses. So when stars are born in the universe, and they are born massive as a large star with a mass that is 8 to 10 times the mass of our sun, lives out its life, burns all the hydrogen, gives you the fusion reactor, goes supernova, and then it can end up either as a black hole or as a neutron star. And so this idea of black holes as dark remnants, these are remnants again, which are the afterlife of stars, was well known in the 1930s. And as you probably all know, it was Chandrasekhar who really came up with this last step, who was able to show that the normal stars that are born with a birth mass that is quite large could end up as a black hole. And I just want to remind you, right, speaking of radical new ideas, you might have all read that he came up with this theory and this theoretical idea in the 1930s. And it took 50 years for the entire scientific community to really accept it. In the meanwhile, of course, there had been gathering empirical evidence. We had found objects in the universe that had all these properties, but it took 50 years. And that's what I mean when I tell you the pace today is really, really different in the kind of progress that we're making in science. So a third way to think about them is this puncture. So you can sort of see that there's three different ways to think about a black hole. A black hole is really a place. So this is just a little sort of schematic that shows you what are the key properties of a black hole. So that dotted line that you see, it's an event horizon, that's the place where once light enters, let alone any matter, anything enters, it can never make its way back. So not even light can make its way back. However, the region where you see, where I've marked as light orbits, that region, if light actually grazes past and it's kind of pulled in by the gravity of the black hole, it can circle forever. It's bound and trapped forever. It's like Dante's Purgatory, right? You're sort of there in limbo. And then, of course, if light grazes past, it escapes the black hole. So here's a nice visualization just showing you how light gets bent around a black hole. These are just light rays. This is a simulation from one of my colleagues. And it's just what you see there as a black disk is the gravity of the black hole. And you can see these are rays of light that get deflected, refocused, and distorted on their way, because you can see space-time itself is distorted, and light, of course, is restricted to follow and paths on space-time. And so this might look familiar to you, because in 2019, you might have seen splattered on the front of most newspapers in the world was an image of a black hole mapping out this region that we saw earlier of light sort of just skirting around the black hole, getting focused and forming this kind of ring. This is the light that is in limbo around the black hole. That's going to eternally circle the black hole. And this is something that we saw. This is data from the Event Horizon Telescope collaboration. And what you saw are the light that is trapped very close, but not quite at the event horizon because you're still seeing it. And that's illuminating the presence of a black hole. So this is how we infer that there are black holes, indirectly from the light around them. Another way in which we have inferred where black holes are, this is the center of our galaxy, and what you see numbered are all the stars. These are real data, individual stars, and that is the date the data was taken. And so this is data from my colleague, Andrea Getz, who is at UCLA. And for this mapping work, mapping the orbits of stars, and that's the time, so this data was taken over a period of 10 to 15 years, this is what she got the Nobel Prize for in 2020, mapping out the orbits of stars around black holes that definitively proved that there was a black hole in the center of our galaxy. And the reason you are able to do that, and many of you who've sort of looked at the solar system, so here's a star called SO2. This is a star that completes a full closed elliptical orbit. So much like the orbits in the solar system, you can then use, for example, as you all know, the orbit of the Earth or Mars or anything to infer where the sun is, right? And so that's what she did. And she was able to calculate the mass of the black hole and show that it was 4 million times the mass of the sun. And yeah, it's a spectacularly large number, but on the cosmic scale, it's actually not that large. The number of stars in the center and in the entire galaxy are, of course, 1,000 times more massive than the black hole itself. But in the innermost region, the black hole dominates, its gravity dominates. As you move further out, the stars start to pick up and they start to get more important. As you move further out, it's the dark matter that takes over completely. So black holes actually grow in two modes. They're either fasting or they're feasting. So when they're feasting, they're actually pulling in a lot of gas around them that is glowing. And you can see that here. And they are seen as quasars, which are sort of the beacons of the universe in the early universe. Okay, you can see that now. Yeah, I got it. Yeah. And then there are black holes like the one in the center of our galaxy, which is actually starved of gas because it has gobbled all the gas that there ever was, and it's just sitting there. And it's only dimly kind of seen in the infrared and radio wavelengths. It's not really seen in the optical wavelengths, the wavelengths that our eyes are actually sensitive to. But as quasars put out all their energy in the ultraviolet, in the range that we can see with our eyes. So this is Hubble Space Telescope data of a quasar. And so quasars are so bright that they outshine the inner part of the galaxy that has the black hole, outshines all the stars in the galaxy that is hosting it. Therefore, we can detect these quasars out to the greatest cosmic distances. These are the cosmic lighthouses. We can really see them way back into the universe. As you all know, one of the most fascinating things about our universe is that when you go out and look out into the night sky, you're actually looking back in time. So the night sky is like a time machine. It's allowing you just from the sun, our sun. If the sun shuts off, we won't know for 8 minutes. And remember, the sun is our closest star. So all the galaxies that you are seeing in any typical Hubble Space Telescope image, light has taken billions of years to reach us. So what does that galaxy look like today? Actually, we have no idea. We know what it looked like billions of years ago when light actually left it. So we are able to map the infant universe, the very early universe, by choosing very cleverly the wavelengths of light. Why is that? It's because even though the quasar, as I told you, when it's feeding, puts out all this energy in the ultraviolet, because the universe is expanding, the light from a distant object on its way to us gets stretched out because of the expansion of the universe. And something that started out very energetic becomes very, very limpid by the time it reaches us. So if we are able to see the universe in the lowest energy wavelengths, the infrared wavelengths, we will be able to actually see the farthest away objects. And that's where JWST opened the windows into the universe. It was the first telescope, space telescope, that was sensitive to the near, mid, and far infrared. For those of you who are nerds, that's microns. We're talking of 1 to 10, 1 to 20 microns, that range. So this new pair of eyes in the universe has revealed, as I'll show you, remarkable new things, completely unanticipated. We had extrapolations from previous models, but this is a view with which we had never seen the universe before. So as we'll see, the universe has thrown up a lot of exciting surprises. So just to give you an idea of what multi-wavelength images, so we are looking at the heart of the Milky Way in different light. So this is in radio light. And you can see, so this is the disk of the Milky Way. We are in a spiral galaxy. This is the black hole that is right at the center. You're seeing all these magnetic fields. It's a very, very messy place, a very complex and messy place. Still, there's a lot of order, even though that was very messy in individual object. When we look at the class of objects, when you look at all the galaxies and we look at the black holes they host in them, there appears to be a correlation between the mass of a black hole and the mass of stars in the galaxy that's hosting it. And this is sort of what came out. This was first published in 1998 when I was still doing my PhD. And it was this plot that really inspired me to get into the idea of black holes, to try and understand, is this a correlation, mere correlation, or is there some causation, right? So is this correlation telling you that somehow the properties of galaxies and black holes are interconnected, or is just happens chance that, it's like randomly we get this correlation? And so what my thesis work involved, we had a pretty good understanding of structure, how it forms in the universe. And my work, done in collaboration with my advisor, Martin Rees, was to embed black holes into the whole cosmic story. Because at that time, black holes were really not known to be a key player. They were believed to be this sort of oddities and maybe quite marginal in the universe. But it turns out, again, that's something that has gotten completely shifted in our understanding. And this graphic that you see is work from one of my PhD students, where we've looked at tracking the evolution. These star-like objects that you see are actually black holes. And what you see is that correlation that I've shown you in a diagram here. That's the real data on the right-hand side. And we are able to reproduce what we see with the classes of models. So remember, in science, especially in a science like cosmology and astrophysics, we cannot do controlled experiments. So what we can do is we have to build models that are calibrated to what is observed. We have to then from those models, we have to make further predictions to ratify the model, right? So that's the kind of logical loop that we have to follow. So one of the other things that we found about black holes is not only do they reveal their presence because of the stars right around them, while they're feeding, some of them actually dribble and they produce these jets. So not all the matter actually gets funneled into a black hole. Some of it gets funneled into jets. So this is also seen. So any theory that combines the properties of galaxies and black holes has to explain this as well. Like why isn't all the matter going in? Why is some of it getting spewed out? And how much gets spewed out? In order to understand that, we need to know how black holes grow. So this is just gas. This is from a simulation that I did a few years ago. This is a cross-section of a disk that is feeding the black hole. And what you see in the center, the black hole's in the center, and the gas kind of eventually trickles and goes down. But black holes also grow in another way. They actually crash into each other. So two galaxies that harbor black holes, and that one's flickering. Again, this is a movie made by one of my former PhD students as well. And so you have two spiral galaxies, like the Milky Way, garden variety spirals that have black holes that are growing in them. That's why they're flickering. Then these galaxies will merge. This happens very routinely in the universe, nothing special. But when that happens, the two black holes will merge. They will crash, they will merge, the two galaxies will merge. And these are kinds of objects we see in the universe. So we're able to explain that as well. Then the question is, something else happens when two black holes merge. So this is the top-down view of that disk in which a secondary black hole, this is another computer simulation that I did with a collaborator a while ago now. And so you see the second black hole spiraling in through the gas disk, and it produces these patterns. It produces this light and dark regions that you can see by eye. And so those are the kinds of regions from which you would get light emission. So we were able to show that we can catch a black hole going around and crashing into a second one by the kind of light pattern that's going to come out when this happens. So this, again, has been detected. So this has been sort of the joy of my life. So this is a paper that we wrote in 2002, and the image that I showed you from the Event Horizon Telescope collaboration, that donut of orange donut, actually ratifies this pattern that we had predicted before. So what happens, something else happens when two black holes merge. And remember, we talked about how black holes can be thought of as punctures in space-time. So this is a rendition. Again, this is a supercomputing calculation that actually took 2 years to do. And so what you see there is space-time. And those punctures, we are seeing them from the top. And so when two black holes merge, they actually cause a tremor in all of space-time. And that tremor is actually measurable. And that's measurable for these supermassive black holes. So black holes in the centers of galaxies that weigh more than 1 million times the mass of the sun are referred to as supermassive. So in order to measure the signal of that crash and the sort of reverberation in space-time afterward, you actually need a system of satellites in space. You can't do that from the ground. We don't have the frequency, the resolution, and the sensitivity to be able to do it from the ground. So this is a mission that Europe is launching, that NASA is involved in. It's called the LISA mission, that is due to fly in 1930s. So you might say, okay, this is great. You're telling us, giving us a primer. How does it all fit in? So This is a simulation of a piece of the universe. Remember, this is the kind of data that we have, controlled experiments that we can do. This is a simulation of a patch of the universe. What you see fuzzily is dark matter. So dark matter is in the driving seat of the universe. Most of the matter in the universe is dark matter. It does not emit, reflect, or absorb any light. It's very peculiar. That's why it's called dark matter. The only way it interacts is via gravity. And we believe that this dark matter is made of particles. Some particle that was made in the very early universe, whose nature we don't know yet. But we know all this that dark matter does. How it manifests in the universe is something we understand really, really well. It's in the driver's seat. It forms the scaffolding in which all galaxies form, black holes form, everything forms, planets form. And we are here because dark matter is doing this driving, gravitational driving. And the regions that you see light that are emerging, those are the regions where galaxies are forming. The first stars are forming, and they are shown as little yellow dots of light. And this filamentary structure, for those of you who have sort of a keen eye, you can imagine that it looks like neurons, right? And you saw something fantastic happen there in the universe. This universe was opaque, and then suddenly at some period of time, there is so much radiation from stars that it becomes completely transparent. And that's a transition that we have been looking for. We have sort of found it, but we haven't quite nailed it. This is a simulation. Okay. So what has James Webb shown us? So James Webb has turned up so many galaxies, more abundant galaxies by a factor of 10 than the most optimistic predictions that we had made from our extrapolation. As I told you, James Webb allows you to look really far back into the universe. So these are some of, I know they look a little unremarkable, but there's a lot of information here because we have spectra. So as you all know, this is just the light. The spectrum is a fingerprint. It's a unique fingerprint of every object, and that can be measured. That is the distribution of energy across wavelength. That allows you to figure out the properties of the population of stars. You can actually pin down the age of stars. You can pin down the combination of stars that are contributing to the starlight. And amid all of these galaxies, these little red things, they're called little red dots. Very unimaginative, but whatever. Each of those actually harbors a black hole. We know that. But what we don't know is of the total light that you see coming out, what fraction is coming from the black hole and what fraction is coming from the star. So that's a big open question. So the thing is that there's a lot more light in the universe than we ever imagined. So many more things are turning on in the early universe. Of course, the big question is, how do black holes form? And so the radical first idea, and I think I alluded to this much earlier, was proposed by Chandra in the 1930s. And he worked out with a clever marriage of the new with classical physics and thermodynamics, he was able to combine that new science, which is quantum mechanics, and was able to predict how a star would evolve in its lifetime. And he showed that the end state of a star would form a black hole. So if you started out with a star that was 10 times the mass of the sun, you could get a black hole that was maybe 5 times the mass of the sun. So his idea, there was much resistance in the scientific community. And in fact, one of the reasons the idea took so long is we didn't have the instruments that enabled the detection of these black holes in the universe. And of course, as data allowed us to find these black holes, his ideas were accepted. So when I started working in early 2000s, as I mentioned, on trying to weave this synthetic storyline of how galaxies and black holes grow in tandem over time, there was a burning question. I always wondered, is there another way to, I know Chandra was great. I am, greatly admiring of him, and I very inadvertently followed in his footsteps in many ways, ending up at Cambridge, England, ending up at Trinity College, ending up as a fellow there. But I always wondered, right, is there some way you can bypass the formation of a star completely and actually just form a black hole? Because as I showed you, there are many ways to think about a black hole, and one way to think about a black hole is to just concentrate a lot of matter into a very tiny space. Can we do this some other way? So 2005 and 2006, I started on this sort of exploring this kind of really bold idea that was seen at the time as very speculative. And everyone was intrigued in the community when the set of papers came in, but they were like, well, this is a beautiful piece of physics, but we don't know if it's relevant for our universe, right? And because the proof is the pudding is really in data. You need data. So but it took us a long time to sort of refine, many generations of my research group, students, postdocs working on this. And so the idea was actually quite simple. The idea is that this is the light seeds, black hole seeds. That's the traditional Chandra way to make little black holes. And so that other part of the diagram is the work that I have done over the past 20 years. Come up with these completely different ways to make the first black hole seeds. And what is special about those other ways is that you can make an initial seed that has a birth mass that is much, much higher than one of Chandra's little black holes. And so you can start with something that's 1,000 times the mass of the sun, 10,000, even 100,000. And the physics was just beautiful. And it turns out that there was an observational reason why this would become important. And I don't know how I sensed it, but I just did. I intuited that if we started finding these quasars that are really bright further and further back in the universe, which we were slowly starting to, in my mind's eye, I was like, if you find the farthest quasar that is powered by a 1 billion solar mass black hole, very early in the universe. So the age of our universe from the Big Bang to today is 13.8 billion years. But we are now able to look back to when the universe, especially with James Webb, when the universe was just 400 million years old, so a fraction of its current age. And I speculated, I said, what if we find an object that is actually a fully grown quasar that's emitting light? Suppose we chance upon a very bright object and we find it, and the mass of the black hole is 1 billion times the mass of the sun. If we start with one of Chandra's black holes, tiny 10 times the mass of the sun, you just don't have enough time in the universe to grow it. I showed you all these ways in which you could grow. You can crash as many as you want into each other. You would just never build up 1 billion solar mass black hole. It's just a lot of matter that you have to push into a black hole. And so the motivation was, what if you could make a black hole that by birth started out with an advantage? And it was born hefty and born heavy. So we came up with these two mechanisms, and then we started working out over the years. And so this is a mechanism that I want to focus on because this is the one that we were able to make very concrete predictions, testable predictions. And so this is called the direct collapse of gas. So in the very early universe, when you form a galaxy, you have this dark matter scaffolding into which hydrogen, so the early universe is pretty much, well, our universe overall is mostly hydrogen. So hydrogen falls in, and it settles into a disk because it has some spin, it has some rotation. And that disk, the way stars form is that disk actually fragments, cools and fragments, and it forms stars. It cools, becomes dense little blobs of gas, and they just ignite fusion, they become stars. But if you can somehow circumvent that process, prevent the disk from actually fragmenting, and somehow you can make all the disk mass go to the center, funnel it right down to the center, then you can make a black hole. And so an analogy of this direct collapse process is a bathtub. So if you're sitting in a bathtub and you're done with your bath and you pull the plug, and you see the water going down very rapidly in a vortex. So something similar to that happens in the very early universe. It can happen. And then all the matter in that little dark matter region, which could have become a galaxy, doesn't form stars and forms a black hole instead. However, this setting, how this happens, is something that we are only now starting to simulate, because the capacity of computers, even with the best, the fastest supercomputers, you don't have the resolution. If you want to resolve a gas packet flowing in from the outside of a galaxy in, and you want to see how it goes all the way into the black hole, you just don't have the compute power yet. So we've got to do a little bit of the problem, and then we've got to chop the box and then focus back in and connect and patch, and then connect and patch. And we're just now able to do that. And we see that this process is actually feasible. So theoretically, we were able to show that this process not only is feasible in the universe, but that it can also happen. There are places in the universe that have all the right properties. There are bathtubs around there where this can happen, right? And that's what is critical in making a prediction. It has to be something that happens often enough that we should be able to see it. If it's a once in a trillion chance, we'll never see it, right? So there's a very specific, pardon the slightly crowded thing, but plot here, but it's a very specific setting in the very early universe that this can happen. So you have a galaxy, a first galaxy that forms its stars, and then you have these little satellite galaxies. This is how structure forms in the universe. You have a big parent galaxy and you have little satellites that are floating around. Because in our universe, structure forms hierarchically. You form little clumps that then get together to make a big clump. So this parent has already gotten its stars, and the stars are irradiating this satellite that has only gas, no stars. And remember, this is the satellite we don't want to form stars in. And the gas will directly collapse, form a black hole, but then these satellites don't last long. They actually crash into the parent. When I say long, in the universe, not long means less than 1 million years, okay? We're not talking human lifespans here, like completely different scale. But then you form this weird object where the light that's emanating from this object is going to be dominated by the matter that is getting pulled into the black hole, the feeding of the black hole, and not the stars, which is the complete opposite of what we see today in the Milky Way galaxy. Most of the light in the Milky Way galaxy is coming from the stars. And the black hole, as I showed you, is sort of fasting. And that's what is the typical situation. So here we have a unique signature of a new kind of galaxy whose light will be dominated by the light that's coming from the black hole. And when we calculated this, we were able to show that what you need to pin down this kind of galaxy is simultaneous observation of such a galaxy by the James Webb Space Telescope and the Chandra X-ray telescope. Because matter falling into a black hole, the matter gets so heated that it actually glows in the X-rays. And Chandra X-ray telescope will be able to detect that. Remember, I told you, you have to separate out the light that's coming from the growing black hole from that of the stars. So this combination, this powerful combination of telescopes will allow us to do just that. So this doesn't matter. This is just for the geeks to show you what our model predictions look like. These are spectra. These are the spectral signatures, what you see as black dots. Anything below the black dot, that's the sensitivity of James Webb. You can see anything that is powering above it. Anything below, any feature that you see below, we cannot detect. Everything above, we can detect. And the sets of lines, the cool lines are the purple-green ones. The warm ones are the orange-yellow ones. These are all direct collapse black holes that we have different predictions for the properties of the different kind of parent galaxy that it falls into. And notice that that's the full range. They all lie above James Webb, so they should be detectable. Meanwhile, if we have one of Chandra's black holes, they would actually be completely undetectable. So this is just, again, showing you the signal that should be detectable with James Webb. And I want you to pay attention to the x-axis at the bottom. You'll see the wavelength is 1 to 10 microns. And I want you to notice that both the red curve in particular, remember, is flat. You see it sort of flattening out. So that's a key feature that we predicted. And so it turns out James Webb is particularly well suited to finding this. And guess what? In 2023, this object, UHZ1, was found. It was seen simultaneously by Chandra and James Webb Space Telescope. And as a gift from the universe, it actually satisfied all 6 properties that I had predicted in 2017, well before James Webb actually flew. You know, doing a post-diction is no fun, right? It's a prediction. And it was just really remarkable. And one of the other things that happened in sort of what aided this discovery, and I keep referring to it as a gift from the universe because of the confluence of conditions that was needed to bring this into view. It's a very faint object, and it was in place 450 million years after the Big Bang. It's a black hole that is 10 million times the mass of the sun. And the reason we found it is partly because of the work that I had done with mapping dark matter, which is the other thread that I work on in the invisible universe. So there are regions in a universe which are replete with dark matter that actually bend light, because you saw matter creates a pothole, and light will traverse that pothole and come back out. And when it comes back out, it's not a black hole, so it'll come back out. And it carries the imprint of that pothole, just as the tire of your car carries the imprint of repeated potholes. Here, light actually carries that imprint. So from that imprint, and the imprint is that you never see the object that is producing the light in its true shape. It comes out in a super distorted shape. So from the distortions, you can back out and you can work out how much dark matter you really have. This effect is called lensing. So it's literally a lens, and we've all played with optical lenses, and remember, they magnify. So these lenses, cosmic lenses, also magnify, and that comes in really handy, because if you have a very faint object in the universe that is really far away, our only chance to see it is if it gets magnified by chance, and that's serendipity. So that's why I keep saying this is like a lot of luck, like, luck, 3 times luck, right? Things really lining up. So this object was detected. It satisfied all the properties, and it also then helped us nail other bits of the theory that, you have to end up today in the situation that we find most galaxies in, where the mass of the black hole is about 1,000th of the mass of the stars. Whereas this overmassive black hole galaxy that has a heavy seed that seeded it in the beginning has a mass ratio where the mass of the stars is either comparable to that of the black hole, or the black hole actually dominates the mass of the stars. And so we know it pins down this part of the theory that tells you that somewhere along the line, because now we have such objects, they have to flip. And they have to change. The stars have to start to dominate. So this has opened up new lines of research, new lines of observations where people can start looking for when that transition happens. When do they flip? When do you start forming more stars than feeding the black hole? And that transition, again, I've predicted that. We're waiting. We'll wait and see. We have some predictions of when that should happen. And this is just for those of you who are sort of aficionados. These are just black hole growth curves. It's just showing you from over cosmic time how a black hole could grow. And that line that you see there with UHZ1 is the object. And we are able to show these various growth curves. More importantly, here is the data. And remember, I asked you to focus on that orange line. And what you see there in red is the model prediction from our paper in 2017. And what you see in the blue dots is actually the data from James Webb Space Telescope. It's unbelievable, the unbelievable match to the models. And the other thing we predicted was the amount of energy that should come out in X-ray compared to the amount of energy that's coming out in the infrared that James Webb is detecting. So this is what Chandra should detect, and that's what James Webb should detect. The models are all the black curves, and the lines that you see in blue are the data. So it's really, really remarkable that all 6 properties that we predicted for such objects that tell you that they were born with a heavy seed that was made out of direct collapse are actually satisfied by this object. So this was, a major triumphal moment, and I distinctly remember one of my collaborators, an observer who had made the observation, calling me and teasing me about it. He didn't tell me this was the actual data. He kind of led me along and said, well, those blue dots that you see there, he said, that's from your older paper. I just like got it off the paper. And I said, well, why did you get that off the paper? I can give you the model. You can plot it, right? And he then said, are you sitting down? Are you calm? I said, yeah, I'm calm. What's going on? And he said, well, that's the data. That's the James Webb data. And your model is the red curve that he then showed me. And he said, it's like remarkable, it's unbelievable. It's at 5 sigma, which for those of you who are physicists in the audience, that's the gold standard in terms of statistical certainty that this object is really so I think what has been really remarkable is that, this one object was revealed to us that there is more than one way to make a black hole. And if you may remember, I showed you there were 2 pictures of two ways of making black holes. One was a direct collapse, and another one that I didn't spend much time on, which is black holes that form in nuclear star clusters. I'm really excited that, watch the news, there may be something else that's coming up. So I think that what has been wonderful about sort of this journey, as I mentioned, is the sort of 20 years within which all of this has come full circle, but also how it has explained almost everything that we are seeing. We are seeing many more black holes, which means there has to be more than one way to make them. And I think now it's opened up all these further new questions about, what fraction of black holes are made by heavy seeds versus light seeds, and are there new ways to dissect, to look at a black hole and the galaxy it's sitting in to figure out how it was made. And, I think for me, it was completely unanticipated. What drives me to do my work is the passion and the joy of figuring things out, the joy of being able to calculate something, to make a prediction. And I've been really grateful that my colleagues have taken all my predictions seriously enough to go and actually go make measurements, right? And to see if it's, so they've deemed the ideas, even though originally people often start out saying, oh, they're a bit, speculative. I've been very fortunate that, ultimately people have believed in my creative capacities and said, you know what, there must be something. If Priya's onto something, let's just go see which instrument we can use to either prove or disprove her. And of course, I would like to say I'm agnostic about whether it's proven or disproven. Of course, it's much sweeter when it's proved right? So, and I think in a completely unanticipated way, the community has rallied behind the discovery, and all kinds of unexpected accolades and recognition of the work have happened, totally unanticipated. But I think, one of the things that I always imagined in an old-fashioned way is that, it would be really important and interesting to leave a legacy, like an intellectual legacy. So by choice, I don't have kids, so my legacy was going to be my work. And I just feel now that, yes, this is going to stay, but this is science, right? You never know. This idea there could be an augmentation of this idea, modification, refining of this idea. We don't know what's in store, but for now, I'm super grateful and really thrilled. And I'm very happy with the universe. I'm not so happy with the world right now, but I'm really happy with the universe, And I think if you want to know more and you thought you want to delve into it, so I did, as was mentioned, I did write a book in which I looked at a lot of these path-breaking ideas in cosmology over the last century and mapping the heavens. And I also wrote a special article that is really accessible with beautiful graphics done by Scientific American, which predates the actual discovery. So this is where all the predictions, so I wrote papers for my colleagues about all these predictions in detail. And because of the really profound implications that if this pathway was actually shown to be a valid one, it has really profound implications for our understanding of the cosmos. So I actually was encouraged to write for the public because this would be, potentially transformative way to think about our universe. So I'll just stop here, and thank you so much for your attention, and I'll take questions. Sí.
Thank you very much, Priyamvada. I think it was a fascinating talk, and you showed how from an idea, and over a period of time, it could be proved that was very much right. There are many things which I would like to ask, but the one thing which is you mentioned about the dark matter, but is there any dark energy?
Yes.
And if there is any relationship, can you explain?
Is this working?
Yeah.
So yes, I forgot to mention, you might have guessed already that whenever astrophysicists put dark as a prefix, it's a standing for our ignorance. We don't actually know what it is. So in fact, in 1998, two independent teams actually discovered that not only was our universe expanding, but the expansion was accelerating. And in order to produce an acceleration, you need some energy. And so we believe that whatever it is, we don't know what it is that's driving this acceleration, but that is something called dark energy. And its nature also remains, again, we know how it manifests, we don't know what it is. That's the big open question. And of course, the dream would be if somehow dark matter and dark energy are related. But they are sort of countervailing each other. So dark matter has gravity, so it pulls things in, and dark energy is pushing things out. So there are a lot of models, a lot of theoretical models. I think there are actually hundreds of them that try to combine the two. There hasn't been one that has been convincing enough to even follow up at the moment. Yeah.
Yeah, thank you. Thank you very much for that. The other interesting thing you said about fasting and fisting black holes. Does it mean they grow and collapse over a period of time?
They do, when they stop growing and they are fasting, they don't actually collapse. The event horizon remains the same size.
Okay.
But you're absolutely right that when they're feasting, they actually grow. And what we mean by that is that the size of the event horizon changes and it becomes much bigger. And when a black hole is actually feeding, the event horizon is actually kind of shuddering from the flow that's coming in. But that is something that we have not yet detected. That's well beyond, in terms of how microscopic that effect is likely to be. It's beyond the ken of any instruments we can build now. But what we do know is that the event horizon size changes and it grows. It doesn't actually collapse. The only time that we think that the event horizon can actually collapse is this beautiful prediction that Stephen Hawking made in 1974 of black holes that you could form very early in the universe, right after the Big Bang. These are called primordial black holes. And these actually could evaporate over time. And they can evaporate because of a very peculiar quantum mechanical process, which is named Hawking radiation after him. So they can actually shrink. So you have to have very minuscule black holes, and those minuscule black holes can actually evaporate. These supermassives, these extremely massive black holes, Hawking evaporation timescales are much longer than the age of the universe. So we would never sort of see them shrinking, but we see them growing.
Yeah. You also mentioned about the galaxies and black hole relationship. What exactly the feedback between the black hole and galaxy or galaxy to?
Well, if I'd resolved that,
Yeah.
I would be walking to Stockholm. So, so this is a big open question.
Yeah.
So we can understand that there has to be a relation is obvious, right? Because it's the same gas that has to feed the black hole, and it's the same gas reservoir out of which the stars form. So obviously, somehow there is a piston that is sometimes pushing the gas in all the way and sometimes not. So this process is referred to as feedback. And how gas actually gets regulated to go all the way in versus hang around outside and cool, fragment, and form stars is the big sort of unsolved question. So our simulations are showing us some kind of signatures that it's a positive feedback loop. But exactly how it works and why it works is something we don't understand. And we think that magnetic fields around black holes, they're very messy, as I showed you in one of the graphics,
Yes.
right? Tangled magnetic fields kind of live around black holes, and they would direct and funnel black holes in funny ways along the field lines and so on. So it could be that, the flows are so complex that because we can't resolve them yet, once we are able to resolve them, we can probably come up with a nice kind of physics explanation. Right now, it's a bit of a hand-wavy explanation.
Yeah, your most of the work, starts from idea to model and then validation. Do you think there is some intuition? I mean, since how the idea came, maybe of course you have certain amount of knowledge, and then because everybody studies the same thing, but everybody is not Priyamvada, So what is that difference? That idea to model, to you may be doing simulations to ultimately the validation. How this process normally follows? You said 20 years in your lifetime, but how the idea germinates, I mean, where it happens.
It's very hard to predict. I wish I could, follow the lore of scientists and say, well, I was in the shower one day and suddenly, it's not like that. It didn't happen like that. I think what it is, as you very rightly pointed out, right? Once you have very solid foundational knowledge, it's almost like composing music, right? So you know music, you know the limits of your instrument, but then it's like jazz, you can improvise on it, but you need to know the music before you can improvise, right? So in this case, I think what really happened was that it was such a given that black holes could form only one way, that, my mind, as a sort of slightly lateral thinker, I was like, let's challenge that, right? Let me see if I can come up with physics. I never actually imagined that I would be able to close this entire arc at that time. And you never know. In science, you never know where something's going to take you, right? As you well know from your own work, right? And your models always surprise you. And it just started from saying, okay, let me just be a little bold and let me play. For me, a lot of this is play. Let me play this game and let me play this calculation, say, well, if things didn't work out in this way, what if I try something else? And then it turns out that, as you said, you have this intuition and you have this inkling when you figure out this other pathway, then the intuition tells you that, okay, Priya, follow this up. This is not a blind alley. You have a lot of blind alleys in science, right? Science. Often scientists present a very sanitized view of their discoveries, and it's very messy. There are lots of dead ends, wrong turns, mistakes in calculations. You have to redo. You have to go back. But I think with this idea, kind of very early on, I could see that I wanted to continue it, and I think I wanted to continue it because it was just too hard. The computers did not have the capacity to do the calculation. So I had to rely on pencil and paper and kind of push, on just analytic models. And then, bam, when it became clear that, okay, I can simulate a version of this, a very simple version. And I think that's where I also credit, MIT, my undergraduate institution, where I really learned how to learn. And you learn how to solve a complex problem by really paring it down. And your intuition tells you what is the essential and what is the inessential. And so you start with a model. And I think I was able to start with a very simple picture, literally the analogy that I was giving with the bathtub, and then build it up to include all the complexities. The gas is rotating, the gas is heating, and it's getting irradiated. All the little pieces were added on. So I think it sort of was really, it sort of developed in fits and starts. It wasn't clean. It wasn't like one day and I had the whole thing out, right? It was lots of fits and starts. There were some frustrating times when, the calculation, I was just not able to simplify some aspect, and I didn't know if that was going to be really important. And if I cannot do that, then I can't do this calculation, right? So there were moments like that. But I think, I've also been really fortunate. I've had fantastic students, fantastic postdocs who really kind of, helped and bounced ideas. I was able to bounce ideas off them. And they are also my biggest sort of critiques, right? If I say, okay, here's a calculation, they would push back and say, well, how about this and how about that? So I had, this very, very vibrant intellectual milieu around me always. That's another sort of real gift, in science. It doesn't always work out that way.
Yes.
So that sort of really helped as well.
Yeah. The last two questions. One is, from Galileo telescope to today, we have advanced, almost a million times better than what it was earlier. What is you do see that what next change may come in the observation? What is the way forward to...
Yeah, that's a great question. So I think instruments and data are really driving this revolution right now. And I think there's two things that are going to happen. First is new kinds of instruments. So that LISA interferometer in space, that little image that I showed you, that will detect the gravitational waves from crashing black holes, that's a whole new window into the universe, which we've not yet opened. And we've seen, we've opened it a slit, and we've seen that these waves exist. And we've seen little black holes crashing into each other. And so we know that this is a phenomenon, it will happen. So I think that's the next sort of frontier. The other frontier is the use of machine learning and AI to mine as much information as we can from any data set. Okay. And the thing that AI is really good at, and all of you may wonder, right? AI has, of course, issues in terms of privacy, encroachment, there are issues of safety of our data and uncontrolled AI. But as you may imagine, a lot of us scientists are very excited about the discovery potential that AI allows you to have. And what it really allows you is, I showed you that one correlation, right? That one correlation that has driven all this work on trying to disentangle, the connections between galaxies and their black holes. What AI is excellent at is finding all kinds of correlations, higher order correlations, not the simplest ones. This is the simplest one that we saw. It's a linear correlation, right? And so AI can help us find these very interesting correlations. Many of them will likely just be happenstance. Some of them, that's what we hope, is actually going to tell you something about a brand new physical law, like Newton's law, that we didn't know about.
Yeah,
right? So I think that possibility is just so exciting right now. So with the existing data and the upcoming data deluge, we have many new space telescopes that are going to be flown soon. There's the Nancy Grace Roman Space Telescope that is going to be launched next year. And ground-based facilities, there's the Vera Rubin Telescope. And these telescopes are going to be surveying the sky every night. And so we can, right now, I'm showing you all these static pictures of the universe. The universe is very restless. It's a very dynamic place. So if you are sampling it every night, you're going to find new things, new phenomena that happen on very short time scales that you've not captured in these static images that I just showed you.
Yeah, you mentioned about many things that physics has no answer today.
Yeah.
Do you think the philosophy or that will take over for those things? Or how do you see that transition?
I think you're absolutely right that science can answer very particular kinds of questions. They have to be posed in a very particular form to be tackled by the sort of experiment, hypothesis testing, that kind of scheme. There are some questions that at any given time will appear to be completely beyond the realm. So, for example, if you go back to 1543, Copernicus reordered the solar system, right? So we moved sun to the center and the earth out. Do you think he could have ever imagined that the human beings at some point in time would fly two spacecraft called Voyager 1, Voyager 2 that would leave the solar system? No. For him, it was imagination, possibly, right, that drove him to do that. So I think there are ideas, for example, what happened before the Big Bang is a big question. It's a fundamental question. But it doesn't look like we can answer it at the moment. And it's a place of great philosophical speculation, right? There are people who don't like one beginning for the universe. There are people who like universes starting and ending, so cyclical universes. And everything is permitted. Any idea you have is permitted because you can philosophize and you can actually accommodate it. There are no constraints, right? There are no constraints from data or from even the laws of physics that you have to follow. So I think there will be some questions that will always probably be beyond the purview of science. I mean, there are some scientists, many of my colleagues, who actually differ. This is a fundamental philosophical divide on whether you think everything is knowable. And I have some colleagues, there are some famous neuroscientists who are friends of mine who say that, yes, in time, with enough computing and enough understanding, we will be able to decode anger. We'll be able to figure out all the neurons in your body that need to fire, all the chemical channels that need to work to produce anger. I actually do not think that everything is knowable. Maybe anger is decodable. I don't have a particular view on it. But I think there will always be things. And I think it comes from a place of cosmic humility. Because why should we, after all, with a gelatinous cantaloupe, the size of a cantaloupe in our heads, be able to figure out everything in the universe, including ourselves? Why? I mean, I don't see why we should be able to do that. So there may be some things that will remain unknowable.
Thank you. Thank you very much. We may have a couple of questions from the audience. Okay, young girl first. Yeah. I'll come back to you. Madam. Yeah, we'll come back.
Priyamvada ma'am, very nice to meet you. I hope your life is as beautiful as the meaning of your name.
Thank you.
And happy Holi, everyone. I'd like to ask you in what ways are you like the universe, and in what ways are you not like the universe?
Oh my God. Gosh, how much time do you have? No, I think the universe, metaphorically speaking, so there's a lot that is hidden in the universe that is extremely consequential, right? And I think that all of us have parts of our lives that are not necessarily even revealed to ourselves, that we don't know ourselves, that are actually quite consequential to who we are and how we operate and why we do what we do, right? So, that's just one of the things that I can think about. And yes, I am pretty restless. You can ask my mother. By the way, this doesn't mean I was naughty as a child. I wasn't. I was a very goody-goody child. I was just very curious and energetic. So I was also restless, like the universe, and energetic.
Thank you. Yeah, madam. Yeah. Yeah, please.
I'm not a scientist or a physicist, but I have a very curious question, because I've been always wanting to know, what are the black holes of Calcutta like? Because I'm a Bengali and I didn't know what black holes were. But you have really whetted my appetite to go into space studies.
Right.
But I would like to know, why is it called black holes? Because you showed us luminosity, so much of, effervescence on the black hole and swirling round.
Yeah, that's a great question. So, from a star, you are actually seeing the light that's emanating directly from the star itself. So you're seeing these visible objects that are producing their own light. In the case of the black hole, you're actually not seeing the black hole itself, you are seeing it backlit by stuff. So it doesn't produce its own light. It's just kind of bending the light that is produced by other objects and rendering it visible, as it were. So it's not actually producing, that region is not producing its own light. So a star, for example, is a fusion reactor, and it's producing all that light by fusing hydrogen into helium, and that's a reaction that gives out energy, and that's why you see stars glowing. So the star itself is glowing because it is an energy source, whereas a black hole itself is not an energy source, and it's not producing any energy of its own, but its gravity is causing the energy produced by other objects to lurk around it, to trap the energy around it, light around it. And that's what we are saying.
Yeah, I think we have last question. Yeah. Here.
Wonderful talk, thank you. And congratulations on your work. I think we should have more talks like this at IIC. I wanted to ask you, it seems that there are obviously a lot more black holes in the universe than was first anticipated. So what happens if our solar system actually comes into direct contact with a black hole, which it seems is inevitable that it will happen? Now, what are the chances for extinction and survival of the human race?
Right. So I think, thankfully for us, even though black holes are ubiquitous, the spaces between objects in the universe is just so large that we are very unlikely to encounter a black hole of any consequence to us. However, if we do have a head-on collision with a black hole, which is extremely unlikely, there's no way out. We're done. Yeah.
I think I have to close because the time. Thank you very much, everybody.
Thank you.
And let's
Thanks, everyone. Yeah.
Thank you for that brilliant talk.
Yeah.
I request our director, Mrs. Shravastav, to come and give the vote of thanks.
Professor Priyamvada Natarajan, Ambassador Shamsaran, President IIC, Trustees of IIC, Dr. Shailesh Nayak, Dr. Meenakshi Gopinath, ladies and gentlemen. We just heard a really mesmerizing and outstanding talk by Professor Priyamvada Natarajan. I am reminded of, my physics teacher in my school. When he came to teach us physics, he asked us, what do you know by physics? We couldn't answer. Then he himself answered, to unveil the mystery of nature is physics. And this is what precisely Priyamvada has been doing. Now this galaxy, the stars, the black holes, these are such things, which are so, difficult to understand. But the manner in which she explained to us, I'm sure all of you were able to get a fair amount of idea about these, things. I am also reminded of a talk delivered by Nobel laureate Venki Ramakrishnan, whom we had invited about a couple of years back at IISc. The subject was as to why countries should invest in science. So he gave a vivid details and explained to us very nicely as to why it is so very important for the countries to invest in basic science, that unless you invest in science, the country cannot go even economically. For economic growth of the country, investment by the country in science is absolutely essential. And borrowing the terminology of Priyamvada, fasting and feasting, he said that all those countries who were feasting on others, that means they were colonizing others, today their economies are in tatters. Examples are Spain, Portugal, etc., etc. And all those countries who actually invested in science and did not, go in for colonizing others, they have really flourished, and today also they are flourishing. Examples they gave us to us, Germany, Sweden, etc. So, what Priyamvada has presented to us really should make us to think seriously as to whether we are really doing justice to this particular subject. And if certainly we are not doing justice, we are not investing enough in basic sciences, perhaps a civil wise should arise at everywhere, so that the powers that be, the governments at every level, they are really made conscious of why it is so important for the country, India as a country, to invest in science. I am really very grateful to Dr. Priyamvada Natarajan for accepting our invitation and being with us here and giving us such a fantastic and informative talk. Thank you, madam. Thank you very much.
Thanks to everyone for coming.
I would also like to thank our president, Mr. Shamsaran, because he is the one who took initiative and helped us in establishing our contacts with Priyamvada. Thank you, sir. Thank you very much. I would also like to thank Dr. Nayak, our life trustee, who has traveled all the way from Bangalore to be with us here today. Meenakshi ji, my special thanks to you, because at 3 o'clock you had a fantastic interaction session that you arranged for the young students, the budding scientists, with Priyamvada ji. I am sure they would have all benefited immensely. I thank you, all of you, ladies and gentlemen, for your gracious presence, and I am sure all of you have definitely benefited with this talk. And we look forward for more, such talks and visits by Priyamvada ji in future. Thank you very much.